Welcome back. Let's wrap up this week. We're going to talk more about relations. So specifically, let's talk about something called an equivalence relation. So we call a relation equivalence relation if the three conditions we were testing for of reflexive, symmetric, and transitive hold. So let me just explain that for a second. Given a finite set, let's talk about what a corresponding graph would look like in order for something to be an equivalence relation. Well, remember the three things that we already talked about last video were that to be reflexive, every A has to go to itself. Boom, like this. And if I have B over here, it has to go to itself. Boom. If I have C down here, it goes to itself. Boom. Okay, so that's reflexive. Check. Next, we have symmetric. Well, symmetric says that if A goes to B, then B must go to A. Check. So we got this relationship going on. Now, technically, I could stop right here, and this graph is reflexive, symmetric, and to be honest, this graph is even transitive. But there's still more to go with it. Transitive says to do transitive. So let's say B to C does exist. Well, that means that C goes to B. But because I now have this thing that goes from A to B, and I have B going down here to C, then transitive says that A must also go to B. Like that. But the symmetric tells me I have to also have another one going back. So you should, if you do all of these, you should end up with this. You should have a bunch of triangles. If two are related, as soon as one attaches to another one, they have to be connected. In fact, the entire graph are going to be clumps that inside here, everything has a loop and is connected. You can do other groupings, but they all are going to be loop, and all the possible arcs are going to be there. That is what it's going to look like if you do a digraph on this sort of situation. So let me just kind of talk about this one. Consider A, B, C, D, E, and let's make up an equivalence relationship by drawing a digraph such that A is not related to B and C is not related to B. So what I'm going to do here, I'm literally going to make the digraph up. So I have to put all my things in here. I have A, I have B, I have C, I have D, and I have E. Okay, A is not related to B, but first off, because it is an equivalence relationship, everything has to have a loop. That's just the very first thing that you have to have to do, and therefore we have now covered our flexive nature. Well, A is not related to B, so that means by the symmetric that B is not related to A. So this also means that B is not related to A, and C is not related to B means that B is not related to C. So there's no edges between these three up here. I could, however, have A be related to E, in which case E is going to have to come back up and be related to A. Similarly, I could have D be related to B, and B has to be related to D. Now, here's an interesting question here. Can E or D be related to C in this situation? And the answer is no. Because if D or E had a connection, well, actually, I do have one correction. D cannot, but E still could, because this simply said that C was not related to B, but it did not say it wasn't related to A. So I could actually add this in if I wanted to add in this one. And then I could have this. And then we're just going to take this one over the top. So we can get through this process by just kind of building it out one at a time and just think about it, about how things are related. And we could actually build a relationship, then come back and analyze it and that say, so I went through and designed all my relations. Now, is it symmetric? Is it reflexive? And so forth. All right. So let's move on to one more. And this is kind of a hard one. So this is a question of, can I establish this as an equivalence relation? Now, part of what's missing on here that got cut off a little bit was you had 5, 5 and 6, 6. And so knowing that you have 5, 5 and 6, 6 over here, then we have the symmetric. So the first thing we can look for is, do we have all the pairs, which is just 1, 1, 2, 2, 3, 3, 4, 4. And if I also have 5, 5 and 6, 6, then we have the symmetric, the reflexive down. So reflexive is done. Reflexive. Reflexive. Check. So now we have to show symmetric. Well, I have 1, 6 here. I would come over here and ask the question, it does 6, 1. Is it also on here? If it is not, then we can immediately throw out symmetric. But let's suppose that it is, because actually it was one of the things. If you look in your book, it's in there for this problem. So we have that. So we come here to 2, 3. This and 3, 2, those are matches of each other. This and this, the 2, 4 and 4, 2 are matches, and the 3, 4 and 4, 3 are matches. So we have all the symmetric down, which gives me actually the symmetric nature. And the last would be transitive. So I'm going to erase all of my wonderful little marks because I'm going to need this to do transitive. And this is where transitive gets a little bit more funky. So in transitive, let's just look at this for a second. One, let's ignore the 1 going to 6 because 6 doesn't go anything else. But let's consider 2 goes to 3. So then I have 2, it's going to 3. And I have 3 going to 4. I have this, and then I have this. The question is, do I have a 2 that goes down to the 4? And we do indeed, it's right there. And that's the thing that tells me that it is going to be transitive. We can do the same thing, obviously, because the reflex, we already did the symmetric part. These things all come back. We can kind of work our way through there. All right, I hope that kind of makes sense. All you're doing is you're testing to see if all the conditions hold based on the values you have in your particular list. So this one, I'm going to break up this problem just like you did the last problem in the last video. So this time, Cameron, you're looking at all the people on Facebook where X follows Y. I know in Facebook you don't actually follow people, but just take with me if it's just a follows, or we could have this to be connected. Is this an equivalence relationship? In other words, if X is equivalent to Y, is Y equivalent to X? If they're connected. I think friends is actually the term on Facebook. If they're X is a friend with Y, is Y a friend with X? So that would be the symmetric, but you remember, to be an equivalence relationship, all the conditions must hold. Now, Alejandro, you get, again, the height people, X, H, Y, if X and Y have the same height. Is that an equivalence relationship? Jackson, you have the taller than one here. And I want all of you to try this one where tilde of Z, A tilde B, if A minus B is a multiple of 5. So A is related to B if their difference is a multiple of 5. Then you have these 3 as well. So Cameron, you have this one, which is dealing with actually pairs that are related to each other. And then Alejandro, you have the floor function. And Jackson, you have this absolute value. So go ahead and try those. Again, you're trying to make sure each one of these things has all 3 of the properties. Now, a key part that we talk about in this is sometimes we tilde is a relation on a set, but we define the set of all relatives. So this little bars around the X literally means everything that X is related to inside the overall set. And A tilde X is the set of all the relationships. So it's a set of sets. That's kind of big thing is to understand. Just like subsets are a set of sets, this is a set of sets. In particular, it's a subset and therefore an element of the power set. We can talk about does it actually equal the power set or not? That's a whole different discussion point. Common notations is sometimes are X bar and RX. The RX is if you're using the R instead of the tilde, and the X bar, I've just seen that it's not as common, but this one I've seen it in a few texts. So here is an interesting question with that definition. Suppose that F is a relationship such that X follows Y on Facebook. Bob, we want to describe what is Bob. Well, that is Bob is quite literally in Facebook all the friends of Bob. Now, this omega F is actually going to be the set of all friend sets. So there'd be a set for if all of you were in a class in here, there'd be a set of friends for Cameron, set of friends for Alejandro, set of friends for Jackson. And even if you had the same set of friends, they would actually be different sets sitting inside here because they'd have a different label because the label is very important. They're slightly different. And they would also be different because if you have the same friends, but you're not friends with each other, then that's possible. But it's kind of the idea that we're going to go out with all this. All right. So just the last couple of problems. So Cameron, we're going to use a relationship now less than or equal to. If X is a real number, what is its this, which again is its set of relatives. So what are all the relatives of X? If X is just some number, real number, and my relationship is less than or equal to. Alejandro, I'm giving you the one where A tilde B, if A minus B is a multiple of 5, that's familiar. I want you to find all the relatives of 1 and all the relatives of 2. Now remember, these occur even if we don't have an equivalence relation. We're just seeing if they're related to them. If there was an equivalence relationship, in essence, all the relatives of 1, if 1 is related to 2, then their relationships would be the same. And so how many different sets of relatives are there for this particular situation? And what are they? That's a little bit more. So I gave you to find 1 and 2. In general, for this thing, how many different sets of relatives are there? And what are they? I mean, different. So they could have the same different labels, but are they the same or not? And last but not least, Jackson, not forgetting you, sorry, is let's let P be the set of people at a party and N be their names again. What would it mean for N to be reflexive? Well, that doesn't seem weird. Something seems weird here. I don't know what's going on, Jackson. Go ahead and do this problem again. But a key theorem to talk about, it's if there's an equivalence relationship, then A, and I kind of mentioned this before, but A is related to B. Sorry, there's a set of relatives of A is equal to relatives of B, and only if A is related to B. If there's an equivalence relationship, the equivalence relationship already gives us the benefit of this. We kind of move forward on this thing. You don't need to prove it. Now, this is another really cool one is that in an equivalence relationship, tilde, the union of all X of all the relatives has to equal A in some equivalence relationship. Similarly, if for all X and Y, by the way, This is true, number one, because even if there is no other relationships, each one's related to itself. So therefore, we have all of them in some set. For all X, Y, and A, either they're equal to each other or they're completely disjoint. So there's completely the same or they have nothing in common. And this is really cool about equivalence relationships is it's almost an all or nothing kind of situation. And then we really love that. And further, we call these things equivalence classes. That's where this comes from. If we have an equivalence relationship, then the relations are called equivalence classes. And we're actually going to move into talking more about what that means in terms of modular arithmetic a little bit. So if tilde is an equivalence relationship on a finite set A, then what is the connection between the equivalence class and the corresponding digraph? So let's think about this for just a half a second. So I have an equivalence class, and I actually kind of hinted at this. If you have an equivalence class, then they're all going to be connected in the digraph. They are all going to be connected and nothing else. This class and nothing else is going to be connected inside that digraph. So you're going to have this equivalence class, let's call it X, is going to make up one little component. Over here, if X and Y are not related, then these are going to be disjoint. So there's going to be no connections between them. And that's kind of the key idea that we get to use when we stop and really think about all these questions. All right, last set of problems for you. I want you to describe, these are all equivalence classes. Hint, I'm giving it away what you guys already did earlier. But suppose that Cameron, X, Y have the same height. Explain what are the equivalence relations. So think about this. What would be the different groupings of people that you would have if you grouped all those that followed this? Same thing, Alejandro. Where would you get, what would these end up doing for you if x squared plus y squared equals x squared? I mean, x1 squared plus y1 squared equals x2 squared plus y2 squared. What kind of this would be? And then Jackson, what would this be like? So when, for what y values for x, and then think about what that would be like in general to compare and understand these things. All right, good luck. Let me know what questions you have. And you got this as we finish the semester.